Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits, and in this particular lecture we will continue discussing about K-maps. As you see in the previous lecture we spoke about K-maps and why K-maps are necessary, how do we minimize number of odd terms and how do we minimize number of literals in each and every product term, right? So in this lecture I will talk about something which would help us which would help us create groupings of K-maps in a better way. So we will talk about two concepts. One is prime implicants and another one is essential prime implicants. PIs, prime implicants, right? So basically finding the best group is even more difficult when we have larger K-maps, right? And one good approach to driving an MSP is to first find the largest possible groupings of minterms, and these groups are something which corresponds to prime implicants, right? For example, let me take a K-map example. So basically if I draw a K-map, right? Now if in this K-map, let's create some entries, right? So let's assume we have something like 1 1 1 1 1 here, 1 here, and 1 here, 1 here, right? So basically I told like prime implicants is something which is like finding the largest possible number of groupings, right? So prime implicant in this case would be something, one of the largest possible grouping over here is this particular grouping, right? The second particular grouping is this particular grouping. Third grouping is right. So is this clear, right? So basically we created the number of maps which are possible and we are trying to find prime implicants, right? So if you see over here, the best for each and every one in the table, we looked for what is the largest possible group which is possible. For this one over here, right? This particular one, this group was the largest one. Similarly for this one, and this one. For this one, there are two possible set of groups, this being the one, this being the another. Similarly for this one, there are two set of groups possible, this one and this one. So all of these are known as prime implicants, right? Whereas essential prime implicants is something, these are like these are the ones which are having only one group and they don't fit anywhere else in the particular plan of things. Basically if you look at this particular one, right, the corner one, this one, this is the only group possible for this one, right? So this is an essential prime implicant. Similarly for this one, correct, only this group is possible. So basically this is another essential prime implicants. So there are two essential prime implicants in this particular set of example, and basically what simply essential PI means is that the final expression needs to have these terms. The final expression cannot do away without these terms, right? So prime implicants, the largest groups for the ones which are present in the entire K-map. So we saw that we have like so many prime implicants, 1, 2, 3, 4, 5 prime implicants we had. Essential prime implicants are the ones which comprises of the terms which occur only once, and those groups are essential for appearance of this particular number, right? And if you see the essential prime implicants over here, we spoke about two, and let's put the numbers to it, right? Let's see, we have w, x, y, and z, 0 0 0 1 1 1 1 0. As we spoke in the previous lecture, this is how we do a K-map mapping where we have only one variable changing. What will be this particular expression? So basically w bar and y bar. Is this correct, right? So this will be w bar, y bar. How about this particular expression? This is like w x bar y, Correct? This is clear, right? So basically y bar and w bar and w bar y, these are essential prime implicants. These are must have in the term, must have in the expression, final term or expression, right? And then we look for, okay, these two entries are pending, and what is the largest possible group possible is this one. We can always say we make a one group over here, we make one group over here, but then this would end up in two terms. What we can do is we can simply make one term over here, and this term would be what? W x z. So this is a concept of prime implicants and essential prime implicants, right? So just to understand understand it correctly, right? Let's have one more example. And the example over here, what we will take is again a four variable a, and what we will do over here is, let's assume the number of ones are here 1, 1, 1, 1, 1, 1, 1. Let's figure out the essential prime implicants over here, right? And just for the sake of nomenclature, wx, yz, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Correct? And what we will do over here is, let's find essential prime implicants. Correct? Okay, what all possible groups are there, right? Essential. Let's look at essential prime implicant. So basically, if I look at this one, right? This one will be captured only in one group. This one. Correct? This is one. Another thing is this particular one. If I look for the largest group, this will be another essential prime implicant. And the third will be for this one, because this one is not there anywhere. So basically, essential prime implicants in this case are three, and all of three I'm able to form the largest possible groups, and we are able to see that, okay, what will be the final output if I, okay, term this as 1, this as 2, and this as third, right? So what it will be, my 1 would be equal to, we have x as constant over here, and as well as y as a constant, so it will be xy plus, what else in the second one? Second one is entire yz, and the third one would be this particular example where we have wx. Correct? So basically we saw we have three terms, and we are able to capture everything in those three terms. This will be the final output. Correct? Sure. Now this is one of the important concepts of implicants and essential prime implicants and prime implicants. Now I want to talk about something called as don't cares, right? While we are trying to minimize our circuits, let's talk something about don't cares. Don't cares simply means these are unspecified outputs for certain inputs. And basically these can be used for minimizing circuit further, and these are represented by something called as x's. And basically what we can do is we can choose whether to treat them, whether to treat this as zeros or ones as per our convenience. Okay, now let's assume one example. Let's assume we have a case where we have f of xyz was equal to m3, which means what? That m3 was x bar by z. So basically this will be something like x, y, z and f. 0, 1, 1, So let's assume this was 1. Alright. And now let's assume that basically if we convert them into a K map, what it would look like. Right. So what this would look like is M3 is nothing but this. But if someone tells me that instead of, okay, so this is 0, 0, 0, 0, 0, 0, 0. What if someone tells me that, okay, there are certain outputs which I don't care for me. Let's assume that this particular output is don't care, then this is don't care, and this is don't care. What would this mean? That M2 is don't care, M4 and M5 are don't care. Can we do a circuit minimization if this is the case? Right, we can. So basically, as I said, right, don't cares are X, these are unspecified outputs for certain inputs. They can help us in circuit minimization further, as we can treat them to choose them as zeros or 1. If this is a X, what if I choose this as 1? I could form this group, and basically my circuit would reduce into X bar pi. Instead of, I can choose to make this as 1, but these will not favor me, or it will not help me in any way, because if I treat them as 1, I would end up forming one more term. I will ignore this don't cares. I will assume that this don't care is 1, and I can minimize my circuit forward from X bar Y bar Z to X bar Y. I can end up saving one AND gate. Correct? Similarly, if I show you one more example of right, basically 16 variables, 4 variables and 16 entries. Let's assume I have something like this: 1, 1, 1, 1, 1. What was my entry? This was one of them, and this was one of them. Right? These were the two groups I was having. Now let's assume someone tells me we have don't cares over here, here, and here. Can I minimize my circuit further? Yes. If I don't minimize it, right? If I have something like WX, Y, and Z, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So what will this term will be? My original circuit was something like, original equation was something like YZ plus this will be something like W bar X bar Z. Now let's assume that someone tells me don't cares are there in the situation, and we end up creating these three x's. So basically, is there further minimization possible instead of this group, right? You can always have this group, right? In case number 2, my output would be 1 YZ plus W bar X bar. Or I can have a third possibility also, where I can simply say, let me not take this black group, I can take this as one group, right? So in third case, my output would be something like W YZ plus the original term plus W bar and Z. So basically, if we say this group is something but W bar and Z. So basically, these are the three solutions possible for this particular set of case, where we have like original situation was something like this, where we had one extra product of literal term over here. In case we started using don't cares, if someone tells me that these outputs are don't care, we can have these two possible. Both of these expressions are correct, right? If you see, both of them are minimum sum of products, and both of these are correct. We can choose any one of these. So this is one of the concepts, right? So, and this is mostly about K-maps, and if at all we want to do, we can do multiple practices going forward, right? I can show one more example. Okay, let's to be on the safer side, right? Let's do one more example of K-map. So let's assume I draw a K-map over here, and then let's assume we have some terms. right? So let's assume we have an example saying we have 1 1 1 1 1 1, alright. Let's assume someone tells us, okay, these two are don't care. Can we do a circuit minimization for this? Can we figure out what is f of x, y, z, and w? Can we figure out this particular thing? For this, right, let's start with the concept of prime implicants and essential prime implicant, which we worked upon, right? For this particular one is captured only in one scenario, and extending this group will not be a possible thing. So this is one of the essential prime implicants. For this particular one, the essential prime implicant would be this. For this set of one, the biggest possible one will be this, and then with one left, we can either choose up one or this one. So these are the set of equations we have over here with don't cares, right? And if we try to figure out what is the output over here, we can simply say, okay, it will be one, second term, third term, fourth term, fifth term. And how about if we have one more case where we simply say, this is one of the cases, right? We will have five terms over here. What I don't cares have helped us is they have helped us with minimizing this particular term, correct? But eventually, if you say they had resulted in us adding an extra term, we don't care. For example, if we don't use this particular block over here, right? We don't include these X terms, we will have less number of terms. Correct? Over here, we ended up adding how many terms? 1, 2, 3, 1, 2, 3. So actually, it's not 4 terms. My mistake is something like 4 terms, right? It's not 5 terms. So but right, in this particular example, this don't cares is not helping us, because eventually if we say it is helping us form a bigger group, but what we have done inadvertently is we have ended up creating one extra groupings which is not at all required if axis would not be there. So the thing which I wanted to show you over here is don't cares can help us, right, minimize the circuit. But do remember the precedence. The number one precedence should be we should have less number of product terms which are all together, and the second thing is number of terms within a literal should be less. So don't care is not helping us over here. If at all we had an example where we said that okay, one was added over here and then there was an X, right? Using don't care would have helped in such a case, because what we would have done is our first group would have been all corners, right? And then what we would have done is like this X would have helped us creating a don't care blocks, right? So this is all about K-maps. We extensively worked upon this. We saw 3 variable, 4 variable K-maps. We looked at how do we group things together, how circuit minimization happens, and what is the role of don't cares. Don't cares can help us, but they don't always help us. Like I showed you an example over here that we end up adding an extra term with the don't care. Stay tuned for the next lecture and have a good day.